All right, so we'll go ahead and get started. Welcome. We are on week two of the NCEES Electrical and Computer FE Exam Power Systems webinar series. Anyone here attend last week's webinar as well? If you don't know who I am, my name is Zach Stone, Internet's most popular online instructor for the NCEES Power PE exam. Of course, we also offer a free FE review course, which this Power Systems webinar series is part of. I'm a professionally licensed engineer in the state of Florida. I've got an ABET accredited Bachelor's of Science in Electrical Engineering. I passed the FE&P exam on my first try. All of my experience comes from the industrial world: hard hat, steel-toed boots, fluke meter, troubleshooting at 2 in the morning, construction oversight, troubleshooting, design, you name it. I've touched it, everything from low voltage controls to 69 kV substations and everything in between, from process instrumentation, motor controls, you name it. I love math, right? I love the math behind electrical engineering, and I really enjoy getting to connect with you guys live and sharing what I've learned in intuitive, easy to understand ways. And I've been in this role primarily focused on helping engineers pass the PE exam and FE exam since 2014. So over a decade of breaking down complex topics into really understanding, into easy ways to understand, to maximize your study time. You can find me on LinkedIn at ZA Stone. You can find me at electricalpereview.com. That's our online class for the Power PE exam. You can find me at electricalfereview.com. That's our free online review course for the electrical and computer FE exam that I assume you're all familiar with, which is, of course, why you're here today. You can find me at ohmgurus.com. This is our new continuing education program. We host two guest speakers each month. Each seminar is 1 hour long. We're approved in all states for continuing education. But first, we got to get you guys past your FE exam, then pass your PE exam. Then you can hang out with us and have some fun in Ohm Gurus in the future. And of course, for any test related questions for the FE or PE exam, you can find me at powerpehelp.com. It's the online free community that we host. It's the most active and online, engaged by number of users, number of posts per day, number of comments per day, community for the P exam and FE exam. If you haven't checked it out, it's fantastic. Typically, that's where I'm hanging out answering questions during the day. All right, so what's on the agenda for this week? Last week, we wrapped up complex power, all of the fundamentals of applying power formulas, difference between sinusoidals and phasors. Now we're going to be looking at balanced three-phase systems, especially delta and Y connections, how they change formulas, what we got to watch out for. Sometimes there's a square root of three we got to remember to apply. So lots of great material tonight with great examples as well. And then coming up, of course, we'll be covering all of the rest of the topics in the exam specifications and reference handbook for power systems for the electrical and computer FE exam. All right, everybody ready? We're going to start with just a brief overview of the delta versus Y connection. I'm going to point out some things to always be aware of. Then on the next slide, we'll start working with examples and we'll use our calculator to see if we can come up with the right values. So first on top, we've got Y connections. On the left, we've got a Y power supply. On the right, we've got a Y load. Now in the reference handbook, it says for a Y connection, the line voltage equals square root 3 times the phase voltage. And we can also call the phase voltage of a Y connection, we can call it the line to neutral voltage. It's the same exact thing, just a different name for it. And then we also have this interesting identity from Kirchhoff's current law that says for a Y connection, the line current is equal to the phase current. So first off, we're going to identify the voltages, starting with the phase voltage first. I'm going to use orange. So we could call this the phase voltage, or we could call this the line to neutral voltage. So that we have enough room here, I'm going to show the phase voltages on the power supply, and then I'll show the line voltages on the load. But, you know, the Y connection, the delta connections, we could identify phase and line on both sides. All right, our first phase voltage from A to neutral, positive on A, negative on the neutral. Next, we've got phase voltage from B to neutral and C to neutral. And again, we would have phase voltages from A to neutral, B to neutral, and C to neutral at the load 2. Now let's look at the line voltages using the color of red. So the line voltage, look, here's one phase of my Y connection on my power supply. Here's another phase. Here's another phase. If I look at the load, here's one phase of my load on A phase, one phase of my load on B phase, and one phase of my load on C phase. When we talk about line values, we're really looking at line to line connections. So my first line voltage is going to be from A all the way to B. Here is the line voltage from A to B. Again, not just looking at one phase, we're looking across both phases, or we can call this line to line. Sometimes you also see it described as phase to phase. Same thing. All right, next line voltage we've got from B to C, and then from C to A. Most important thing, again, look, the line voltage, it's bigger for a Y connection by a factor of the square root of 3 times the phase voltage. All right, now let's look at this identity down here. Why does the line voltage equal the phase voltage for a Y connection? Any ideas in the chat? Any ideas in the chat? So the easiest way I like to demonstrate this is first, let's just trace out the phase currents. So here's the A phase current on our power supply, I phase. Here's the B phase current on our power supply. Here's the C phase current on our power supply. Notice on the power supply, it's leaving from the neutral. All right, looking at the right on our load, here's the A phase current on our load, this time flowing into the neutral. Here's the B phase current on our load, flowing into the neutral, and our C phase current on the load, flowing into the neutral. Here's our phase current. Let's identify now the line current, and even more so, why these two are equal for a Y connection. So here's my A conductor first. These diagrams are going to get real messy. Here's the conductor for the B phase. And last, here is the conductor for our C phase. Going from capital C at the power supply to lowercase c at the load. Now, what do you notice about the YY connection compared to the conductors that are connecting our power supply on the left to the load on the right? Any ideas, especially related to the line current and phase current? How about this? I'm going to draw, here's the A line current. I'm just going to call that IL. We call it I capital A to lowercase a, same thing. Here's the B line current. And here's the C line current. All right, well, we're all done. What do you notice about my phase current leaving my power supply, my line current traveling through the conductors from the power supply to the load, and then last, what do you notice about the phase current on the A phase at the load? They're all what? Yeah, they're all equal, said Jamie. Look, if I trace these out, notice how I can connect these. And essentially, since there's no other node for the current to divide off into, there's no other node, there's no other fork in the road, there's no other tree branch. Look, the phase current leaving the power supply is equal to the line current traveling through the conductors. And again, there's nowhere else for the current to go, so it's also equal to the phase current going back down into the A phase on the load. So this is really a Kirchhoff's current law. Since there's no other current entering or leaving, it's all the same. It's all identical. All right, next let's look at our delta connection down here. So we're going to start with What do you notice about the voltages, right? Before, for the Y connection, line voltage was bigger than the phase voltage by the square root of 3. But now for a delta connection, line voltage and phase voltage, now the voltages are equal. And instead of the voltage being bigger by the square root of 3 compared to the phase voltage, now we have that same relationship for the current. Now the line current is bigger than the phase current by that square root of 3. So your voltage and current relationships, when you look at delta versus Y connection, when we're looking at the magnitudes, they're opposite. All right, picking on the voltages first, let's see if we can identify why the phase voltage of a delta connection equals the line voltage of a system. All right, looking at the delta power supply on the left, here's the A phase voltage. It's really important when you hear the word phase in electrical engineering and power engineering, we're talking about this right here. That's one phase of a three-phase generator, or that's one phase of a three-phase transformer secondary. Same thing when you hear the word phase for a load, here's one phase. When we use the word phase, we're really talking about the load, we're talking about the power supply. So here's the A phase voltage at the delta power supply. Here's the B phase voltage. Here's the C phase voltage at the power supply. And then we can do the same exercise at the load. Here's the A phase voltage at the load, B phase voltage at the load, C phase voltage at the load. Now, what happens when we show the conductors? Here's the A phase conductor. Here's the B phase conductor. And here's the C phase conductor. Who here likes the Y connection better? And who likes the delta connection better? Typically, the Y connection is easier to learn, and most mistakes come from the delta connection when you're first learning this. So again, I really like to draw out the conductors. It really helps to see where these relationships come from, especially the ones where the voltages phase and line are equal for the delta and the currents phase and line are equal for the Y connection. All right, we've got our A phase conductor, B phase conductor, C phase conductor. Let's measure the line voltage. We can call it the line to line voltage, phase to phase voltage, or just the line voltage. So the A line voltage, it's like measuring, if I take a voltmeter and put the positive terminal on my A conductor and the negative terminal on my B conductor, that's my line voltage of my system. What do we notice? Before, compared to the Y connection, the line voltage and phase voltage were not equal, right? Here's the voltage across my A phase, but then here's the line voltage, right? We've got line voltage from the A to B conductor was really the voltage across the A phase and the B phase. But now, when we look at our delta connection, look, my line voltage from the A phase conductor to the B phase conductor down here, is it equal to the voltage across just my A phase? Yeah, it sure is, right? Essentially, these voltages are in parallel, right? If I put a positive voltage polarity terminal here for a voltmeter, it's no different than if I put it right on this A terminal or even right down here. Same thing, the negative voltage polarity on the B conductor measuring the line voltage, it's no different than if I put the negative polarity meter here or even here. These are all exactly in parallel. They're equal. So for the delta connection, there's no difference between the line voltage across the conductors compared to the phase voltage across just the power supply or the load. Instead, now we have a difference when we look at the phase and line current. So first, we're going to draw out the phase current in green. Starting with the power supply, here's the phase current on A phase, phase current on B phase current on C phase. Now, I could call this, I'm sorry, I said that backwards. We've got, here's the A phase current, B phase current, C phase current. There we go. So I'm just calling these I phase for simplicity. On the FE exam, you're mostly just working with balance systems. When you get to the P exam, sometimes it's more helpful to call this maybe I BA. This could be I A to C, and then last I C to B. We could name them more accurately, but FE exam, mostly just working with balance systems. So it's easier to simplify. All right, on the load, here is the A phase current. Again, just calling it I phase for simplicity. Here's the B phase current from B to C, C phase current from C to A. All right, what do you notice compared to the line current traveling across the conductors? Is the phase current and line current still equal to each other, similar to the Y connection? Not anymore, right? Why not? Before, Before there was nowhere else for the phase current to go, right? If I look at my Y connection, phase current leaving the power supply, it's equal to the line current traveling from my capital A to lowercase a conductor, and then it's equal to the phase current entering the load from lowercase a to neutral, right? There was no other wires, conductors, terminations, or nodes to divide that current anywhere else. No longer true for the delta connection, right? Look, if I look at my A line current on my A phase conductor from capital A at my delta connected power supply to my lowercase a at my delta connected load, look, I've got a phase current entering this node right here. And then I also have a phase current leaving that node, right? You have a bit of a current divider at this node. So the phase and line currents are no longer equal, but you still have this relationship where the line current is bigger by the square root of 3 times the phase current. The line value is bigger. This time it's current instead of voltage. All right, let's see if we can work some examples, plug in some numbers on our calculator, and make better sense of these delta and Y connections. So on the next page, our first example, I've got the same Y formulas from the reference handbook we just looked at. I've got Ohm's law that appears, I believe, in the resistivity portion of the reference handbook. We're going to be using this as well. And we've got some diagrams here to help us out. Let's see, the example says a balanced Y connected load has a line voltage of 408 volts and a per phase impedance of 10 plus J5 ohms. Determine the line current magnitude. Now, right off the bat, last week we learned about the difference between sinusoidal signals with maximum or peak values and phasors, complex numbers, which are RMS magnitudes with angles. Do we think this is a sinusoidal signal, or do we think we're working with phasors and complex numbers? How can we tell? When we're dealing with power, we're almost always working with RMS values. And we talked about it last week. Really, the only time we work with sinusoidals and peak and maximum values is really when we're looking at power electronics, things like rectifiers, inverters, and we're looking at the signals with respect to time. Another way you can tell this is RMS values is 480 volts is a very, very common three-phase voltage, right? It's common in commercial and industrial. Another great clue. Great job, Daniel. Yeah, this J operator here tells us this impedance. I mean, this is clearly a complex number in rectangular form, a real component 10 plus J times 5, the imaginary component, which is another clue. We're just working with complex numbers. All right, let's figure out the line current. So to do that, this is a load. I'm going to draw a conductor entering this load. I'm going to make it black. So we're really looking for what is the line current drawn by this Y connected load. We'll see what else we can fill in the problem. Line voltage of 480 volts. Well, I can show that from A to B. So here's our line voltage. BL equals 480 volts. This is just like we drew on the previous page. We'll make this red to stand out. And of course, we have 480 volts, not just from A to B. We also have 480 volts from B to C and C to A. I'm just going to show it. I'm just showing my A line voltage here since it's redundant anyways. Last, we have an impedance. If I have a Y connected load, notice how they said a per phase impedance. Was this redundant? What if they just said, hey, a Y connected load, it's balanced, 10 plus J5 ohms. Do I got to multiply that by 3, divide by 3, anything like that? Your impedances are always what? It's always a per phase value. So even if they didn't say per phase, it's still implied. If you have a Y connected load that's balanced, meaning it's the same impedance in each phase, then whatever numbers they give you for the impedance, that's exactly what you have in all three phases. For example, here's my Y connected 10 plus J5 ohm load. That means I've got 10 plus J5 ohms for ZY from A to neutral. I've got the same value of 10 plus J5 ohms for ZY from B to neutral. And I've got the same 10 plus J5 ohms on C phase for ZY from C to neutral. This is what it means by a balanced load. The impedance is the same in each A, B, and C phase. All right, I'm looking for the line current. I'm going to simplify this. Let's look at just the A phase. So I know I've got 10 plus J5 ohms from A to neutral, right? That's ZY. We're asked to solve for the line current magnitude. What does the line current equal for a Y connection? What did we just learn on the previous page? The line current is equal to the what? Line current's equal to the phase current. So I'm going to draw a current angle from lowercase a to lowercase neutral. Again, we're just looking at this portion right here. But I know this is the same thing as the line current. It's the same thing as the current entering right here. All right, how do we solve for this value? If I want to use Ohm's law, right, V equals IR, we can rewrite this solving for the current I. Which voltage do I need to use? Am I going to use the voltage from A all the way to B? That's the line voltage. Or am I going to use the voltage just from A to neutral? So we're solving for the line current. Line current's equal to the phase current. I know the impedance from A to neutral. If I want to solve for the current from A to neutral, that means I need to use the what? That means I need to use the voltage from A to neutral. I got to use the phase voltage of my Y connection, not the line current. Does that make sense? Got to use the, excuse me, I got to use the phase voltage. So the first step, right? Ultimately, we're going to use Ohm's law. The first step is to convert our line voltage from A to B to the phase voltage from A to neutral. All right, back to our Y formulas, right? Line voltage equals square root of 3 times phase voltage. I can solve for the phase voltage by dividing the square root of 3 into the line voltage. So phase voltage equals, here's my line voltage, 480 volts, divided by square root of 3. What does everyone get for the phase voltage in their calculator? What is 480 volts divided by the square root of 3? Does everybody get 277 volts? Great job, Chuck. There's the phase voltage. So now I've got the voltage from A to neutral. I know the impedance from A to neutral. That was given in the problem. That's our ZY. I can use Ohm's law to find the current from A to neutral, which we can call it the phase current. We can call it the line current. Same thing. Now, before we use Ohm's law, right? In the reference handbook, Ohm's law is V equals IR. Does anyone know a better variable instead of R to use for Ohm's law? I've got a complex impedance, right? 10 plus J5 ohms. The resistance is just 10. Can I use just 10 in Ohm's law to find the phase current or find the line current? Nah, I got to use the entire complex impedance, the entire 10 plus J5 ohms. So we really got to use complex Z instead of R. All right, we're setting Ohm's law equal to the current. Current equals voltage divided by impedance. Current equals voltage divided by impedance. I'm solving for the line current, which is the same thing as the phase current, which means I need the voltage from A to neutral. That's my phase voltage. not my line voltage from A to B. So this is the phase voltage. And then last, I need the impedance from A to neutral, which is just what? That's just the Y impedance. So in Ohm's law, we're going to take our phase voltage that we just calculated, and we're going to divide it by the Y impedance given in the problem, 10 plus J5 ohms. That's going to give us the phase current, also going to give us the line current, same thing. So really the only step left in my calculator is I'm going to take this value and I'm just going to divide it by 10 plus J5. Now I'm in polar mode, right? We talked about that last week. I like to stay in polar mode. So this calculator is going to give me an answer in both magnitude and angle when I hit enter. When I hit enter, it gives me a complex number in my calculator, but I'm really only concerned with what? I'm really just concerned with the magnitude. So I'm ignoring this negative 26.5 degrees. My final answer is going to be a line current magnitude of 24.8 amps. When you are ready to study for the P exam, you're going to have a lot more problems, and you're going to have a lot more familiarity dealing with the degrees in addition to the magnitude. But for here, FE exam keeps it simple. Good job, Gid. Everyone else get the answer correct, 24.8 amps. All right, that's a Y connection. Let's try a delta connection. Here's our example. The phase current drawn by a balanced delta connected load is 55 amps. Calculate the magnitude of the line to neutral voltage drop across each conductor. Now, this is a fun one. We're tying in delta connections from balanced three-phase systems into voltage drop, which is also part of the exam specifications. So in the problem, they gave us a diagram. We've got a balanced delta connection for the load. Here's the conductor in each phase. Notice the impedance of each conductor is given 0.2 plus J 0.2 ohms. First thing we've got to figure out is what's the line to neutral voltage drop? The problem was nice to tell us, hey, that's the voltage drop across each what? Across each conductor. So here's the voltage drop. We're going to call this VD line to neutral. That's the voltage drop across each conductor in our three-phase system. So we're looking for this value right here. Could I use Ohm's law, V equals I times, not R, I times Z? Could I use Ohm's law to solve for this? Here's the V I'm trying to solve for. Here's the Z across it. What else would I need to know? What's missing from Ohm's law to be able to calculate VD line to neutral? We got to calculate what? Got to calculate the current flowing through the conductor from here to here to use the impedance from here to here to calculate the voltage from here to here. Which current is this flowing through the conductor? Is that the delta phase current given in the problem, or is that what? That's our line current. So I got to calculate the line current first, then I can use Ohm's law for the line to neutral voltage drop. How do I calculate the line current of a delta connection? Well, I know the phase current inside the delta is how much? That's going to be 55 amps, right? Here's the phase current from A to B, phase current from B to C, and phase current from C to A. How do I convert the delta phase current to line current? I just multiply it by what? I multiply the phase current by the square root of 3. 55 amps is our phase current multiplied by the square root of 3 gives us our line current. So back in my calculator, let's ask it, what's the phase current 55 amps times the square root of 3? We get 95.3 amps. Again, this is the line current of our system. That's this quantity right here. And now I can use what? Now I can use Ohm's law to solve for the line to neutral voltage drop. Ohm's law, V equals I times Z. If I want this voltage across this conductor, which current am I going to use? I got to use the current that's flowing across that conductor. I got to use the line current we just solved for, not the phase current. And then last, which impedance value? I'm not using the delta impedance. I'm not looking at the voltage across the load. I got to use the impedance across my conductor. We can call that Z line. So all we're going to do is we're going to take our 95.3 amps line current that we just solved for, and we're multiplying by the conductor impedance given right here in the circuit. We're multiplying by 0.2 plus J 0.2 ohms. What does everybody get for just the magnitude of the line to neutral voltage drop? So my calculator, here's my line current. Just going to bring that back down. I'm going to use a parentheses and say, hey, let's multiply that by zero point 0.2 plus J 0.2. And again, we got a magnitude for our line current. We got a complex impedance. When I multiply the two, I'm going to get a complex number for my voltage drop. All I'm concerned with is what? All I'm concerned with is just the magnitude of the voltage drop. I need to include the entire complex impedance to get this correct magnitude, right? But all I'm concerned with selecting on the exam is the magnitude. So line to neutral voltage drop is about 27 volts, right? We'll call that 26.9. 26.9 volts are being dropped across each conductor as the current on A phase, B phase, and C phase flows from the power supply to the load. Good job, kid. Wonderful. Easy enough. You know, the great thing about the FE exam, most of the problems are going to be quick and simple. You're only looking at a couple of steps. The P exams when we get to a lot more complicated problems. So most, especially for power systems, it's just one subject. But you got to know how to use all of these different formulas in many different ways, which is exactly what we're going to be doing here today. All right, let's look at the next example. We're on page 7. So page 7, we're looking at equivalent impedances. So the formula reference handbook says we can calculate the delta equivalent load or the delta equivalent impedance by multiplying our balanced Y connected impedance by 3. Someone give me a complex impedance in the chat for the Y connected load. Make it positive so it's an inductive lagging impedance, and just use single digits for the resistance and reactance. What do we got? What value do we want to use for the Y impedance? Let's see. Daniel said 6 plus J9. Sure. ZY equals 6 plus J9 ohms. If I have a balanced 6 plus J9 ohm Y connected impedance, do I need to divide that by 3, multiply by 3, divide by square root of 3, multiply by the square root of 3 to find my ZY? Or is this value what? This value is always a what kind of value? It's always a per phase value. Ooh, careful, Daniel. Not multiplying by 3 yet. We're going to get there soon, although I think you were probably talking about this delta equivalent load. But to complete our Y connected load, look, that means I've got 6 plus J9 ohms from A to neutral. I've got 6 plus J9 ohms from B to neutral. And I've got the same 6 plus J9 ohms from C to neutral. All right, let's convert it to the delta, important vocabulary word, equivalent load or the delta equivalent impedance. All we're doing is multiplying by 3. 3 times ZY, 3 times 6 plus J9 ohms. What do we get for Z delta? In my calculator, I've got 3 times 6 plus J9. Simple numbers, we could probably just do it in our head. Now again, I'm in polar mode in my calculator. So when I click enter, it's going to give me the impedance with magnitude and angle. Impedance, do we typically represent it in polar or rectangular? Impedance, we really represent it in rectangular most of the time. So I'm going to go into my complex menu, and I'm going to go to number 5, A plus BI. That's the shortcut to convert to rectangular. So Z delta, the equivalent delta load is 18 plus J 27 ohms, which is the same thing as 3 times 6 is 18 ohms for the resistance. 3 times 9 is 27 ohms for the reactance. So I've got 18 plus J 27 ohms. We've got this value from A to B. We've got this value from B to C. And we've got this value from C to A. All right, can we do this backwards? Now I have an 18 plus J 27 ohm balanced delta connected load. So now Z delta equals 18 plus J 27 ohms. How do I convert it to a Y impedance? So this is the formula reference handbook. To solve for ZY, we're just going to divide Z delta by 3. So now we're taking our balanced delta impedance, and we're dividing by 3. We're doing the same steps, just in reverse. So my calculator, 18 plus J27, divide that by 3. I'm in polar mode. So I'll tell my calculator to convert to rectangular, and we get the Y impedance that we started with, 6 plus J 9 ohms. Everybody with me so far? So when we convert the delta load to its Y equivalent load, we have 6 plus J 9 ohms from A to neutral, 6 plus J 9 ohms from B to neutral, 6 plus J 9 ohms from C to neutral. Now, really important, right? This math, super simple, but it's important to understand what is an equivalent load, what is an equivalent impedance. So we use equivalent impedances, mostly converting from delta to Y. Typically, we use it for the single phase equivalent circuit. You'll get a lot of practice with this when you are ready to take the P exam, but it just simplifies three-phase analysis. Sometimes delta connections are harder to work with than Y connections. So it's not like, maybe I've got a motor or transformer. I'm not really opening it up and rearranging the impedances per phase, right? This is just the word equivalent means we're really just modeling, hey, if I had a Y impedance instead of the delta impedance, how big would that Y impedance be? Or hey, if uh, if this Y impedance was a delta impedance instead, how big would that delta impedance need to be so that essentially there's no change seen by the system? So I can use it to simplify analysis. So this vocabulary word here is really important. Equivalent loads, equivalent impedances, same thing. When we supply them with the same amount of voltage, they're going to draw the same amount of both power, complex power, and current, complex line current seen by the system. So it's like, hey, if I had a part that was easier to analyze on paper instead of this more complicated delta one, what would the size of that part need to be so that I can swap it out without really changing the system? That's all these equivalent loads, equivalent impedances are. That's it. All right, coming up, we're going to look at our three-phase power formulas. Similar to the ones we learned last week. So last week we looked at S equals V times I conjugate equals P plus JQ. Really important. This formula right here is only for what? This formula is only for single phase. So we're going to look at the three-phase version of this formula on the left. Now, when I look at just P plus JQ, this could be what? Complex power equals P plus JQ. This could be three-phase, or it could be a single-phase formula, right? If I've got single-phase P and single-phase Q, I'm going to calculate single-phase S. If I have three-phase P and three-phase Q, I'm going to calculate three-phase S. So P plus JQ, it can be for three-phase or single-phase. You just got to watch out what you're plugging in. Everything else, these are all three-phase formulas only. Three-phase formulas only, single-phase formula only. Um, this second formula right here, it's important to know that these are magnitudes only, not complex numbers. I find the reference handbook does a poor job at differentiating between complex numbers and magnitudes. I'm always going to try to call them out. Otherwise, it can be a little confusing when you're learning this stuff. So this second formula here in the middle, this is magnitudes only. Magnitude S equals 3 times magnitude V phase times magnitude I phase, or magnitude S, this is three phase, equals square root 3 times magnitude VL magnitude IL. So this is a three phase formula. And then this one down here, complex power equals 3 times complex phase voltage times the conjugate of the complex phase current, or it equals this formula right here. I'm going to recommend trash this formula. Don't use it. You don't need to. It's confusing. You're more likely to make mistakes. Eliminate it from your mind. You'll never need to use it. All right, let's try this example, and we're going to talk about which formulas we're going to use and why. Example says a three-phase circuit, so we're dealing with three-phase, has a real power of 15 kW and a reactive power of 5. This should be VARs. I meant to upload the updated slides, so sorry about that. This is 5 VARs. All right, determine the apparent power and power angle. So first thing, I'm given what? I'm given P and I'm given Q. So which formula am I going to use? I'm going to use this formula on the top. S equals P plus JQ. I'm going to be really careful to remind myself this is complex power and we're working with three-phase numbers. So complex three-phase power equals three-phase real power plus J times three-phase reactive power. So straight from the problem, three-phase real power is 15 kW plus J times 5 kVAR. All right, how do I convert this to get the apparent power and power angle? Who can tell me what kind of number is this? 15 plus J5. Is that a polar complex number or is that a rectangular complex number? That's rectangular. So all I got to do is use my calculator to convert it to still working with three-phase reactive power, excuse me, three-phase complex power. But now we're going to use our calculator to convert it to polar because polar is going to give me the magnitude, which is apparent power, and it's going to give me the power angle. So again, in my calculator, I'm already in polar mode. I'm in R angle theta. So all I have to do is type in 15 plus J5. And when I hit enter, my calculator is going to say, hey, you just gave me a complex number. You gave it to me in rectangular, but your settings are set to polar. So you must really want that number in polar mode instead. You must want to convert the real plus J imaginary component into magnitude and angle. So reading from my calculator, the magnitude is 15.8. What are my units? I've got kW and kVAR for P and Q. What's my unit going to be for magnitude S? Good job, Jennifer. Yeah, not just voltamps. It's going to be K, kilovoltamps. And then what's the angle? We've got 18.4. I'll just round that to the nearest degree. We'll just call that 18 degrees. All right, so the magnitude of our three-phase complex power, also known as apparent power. Remember, apparent power is just the magnitude. Complex power is either magnitude and angle or real plus J times the imaginary component. All right, here's apparent power, 15.8 kVA. Here's our three-phase power triangle. And here's our power angle, 18 degrees. Again, all we did was just use the calculator. We could have used the Pythagorean theorem, right? A squared plus B squared equals C squared. then take the square root to get 15.8. But why waste time? Calculator is going to do it for you in 2 seconds. All right, next problem, similar. Let's see which formulas we're going to use. And again, I apologize. This is kvar, not watts. All right, problem says, again, we have a three-phase circuit once again. Same numbers. Look, 15 kW for my real power and 5 kvar for the reactive power. But now the problem's asking for what? For each individual phase, determine what's the apparent power, what's the power angle, what's the real power, what's the reactive power. What's this problem really asking for? What complex number do I need to know in order to know either the apparent power and power angle in polar or the real power and reactive power in rectangular? The problem's asking for the complex power in rectangular or polar, but it's not asking for the three-phase complex power. It's asking for what? It's asking for the complex power for each individual phase. Great vocabulary word for this is it's asking for the per phase power. It's asking for the quantity in each individual single phase that makes up our overall three-phase circuit. So what's the identity there? How do we figure that out? Look at this formula right here. Complex power, this is three-phase, equals 3 times the phase voltage and conjugate of the phase current. What's the only difference when I look at this formula for three-phase compared to this formula for complex single-phase power? What's the only difference? This is phase voltage and phase current. Yeah, 3 times, said Daniel. Yeah, so great identity is complex three-phase power equals 3 times your complex single-phase power. Or I can figure out the complex power in each phase of a balanced three-phase system by just dividing my three-phase complex power by 3. That's all there is to it. All right, let's try it. First, in rectangular format, our complex single phase power, what the problem is asking for each individual phase, that's per phase or single phase power. All I got to do is take the complex three-phase power and divide it by 3. We're going to use rectangular form on the left to get the real and reactive power first. So the problem gives us, look, 15 kW and 5 kVAR given in the problem. Is that the three-phase real and reactive power, or is that the single phase per phase, or the amount in each individual phase of real and reactive power? If I have a three-phase circuit, and I have a three-phase circuit that has 15 kW and 5 kVAR, that's what? That's already the three-phase values given. So we're going to take our three-phase P and our three-phase Q, and we're going to divide it by 3. So 15 kW, that's three-phase P, plus J times 5 kVAR, that's three-phase Q. Divide it by 3 to get single-phase power. All right, using my calculator, I'm going to type it in just like it looks. 15 kW plus J5 kVAR divided by 3. Again, I'm in polar mode. So the calculator is going to give it to me in polar. I got to go into my complex menu and tell it, hey, I actually need it this time in rectangular form. And we get what? 5 plus 5/3, which is the same thing as we've got 5 kW, which is 15 divided by 3, plus J times about 1.7 kVAR, or 5/3, same thing as 5 divided by 3. All right, how do I find my single phase real power, single phase reactive power? Well, my single phase real power is going to be just 5 kW And my single phase reactive power is going to be 1.7 kVAR. This is just our complex single phase power, or the complex per phase power of our three-phase system in rectangular form. That's all. So we got real power and the reactive power in each individual phase. Now let's determine the apparent power and power angle in each individual phase. So I'm going to start with this. Look, I've got the complex single phase power in rectangular form. Can I just use my calculator to convert it to polar? So in my calculator, again, I'm already in polar form. So this 5 plus 5/3 in rectangular or single phase complex power, I'm just going to press enter. And my calculator knows I want this in polar form because that's the settings I have set under mode, R angle theta. So in polar form, we can convert 5 kW plus J 1.7 kVAR to polar, and we get complex single phase power of, looks like what, 5.3. What are my units? S is unit of voltamps. And if I started with kilowatts and kilovars, then this must be kilovoltamps. So 5.3 kVA, angle, let's see, 18.4, and we'll keep it at 18 degrees. All right, what's my final answer for the apparent power in each individual phase and the power angle in each individual phase? All I do is what? I take the magnitude of my single phase complex power. Magnitude of single phase complex power is apparent power, and I take the power angle, 18 degrees. Does everybody get the same answer in their calculator? Good job, Gid. Good job, Daniel. Now, what do you notice about the power angle when we're looking at three phase versus per phase, or the individual value in each phase? What do you notice compared to the apparent power, reactive power, and real power per phase values? All three of these, we got them by dividing their three phase value by 3. Is that true for the power angle? Ah, Gid said the angle is the same. Great. Yes, there's no change here. In other words, my per phase power angle and my three phase power angle are the same. Your three phase power angle actually comes from the power angle in each phase of a balanced three phase system. Everything else we got by dividing by 3. All right, let's see what else we got coming up. We'll look at our next three phase example. How's everyone doing? Everyone following along okay? Again, power on the FE exam, easy stuff. You're looking at really easy plug and chug problems as long as you're familiar with the fundamentals that I'm showing you here today. All right, we've got our same formulas from the reference handbook. Here's the formulas for three phase. This is the formula for single phase. We're also going to use a little bit of power factor that we learned last week. So this example on page 10 says a balance. We have a three-phase load is rated for 208 volts and 0.85 lagging power factor. The load draws 10 amps of line current. Determine what's the total apparent power, power angle, real power, and reactive power. So first thing I'm going to do, I'm going to draw a quick sketch, right? Here's a simple single line diagram. We got some kind of load. Maybe it's a motor, maybe it's a transformer, maybe it's a panel. Who knows? This is my bus on top. That's the power supply essentially. So we've got a three-phase load. Do I think the voltage on this bus, 208 volts, is that line voltage, line to neutral voltage, or phase voltage? A three-phase load, can I supply a three-phase load with single-phase voltage? Can I do that? No way, right? Three-phase load needs line voltage on all three phases. So that tells us what? That tells us this 208 volts, this is line voltage. So here's the voltage being supplied to the load at the bus, at the panel. This is going to be our three-phase load down here. And according to the problem, the three-phase load draws, you've got a line current magnitude of 10 amps. I'm just filling in the values from the problem at a lagging 0.85 power factor. All right, we want the apparent power, power angle, real power, and reactive power. What single complex number tells us all four of those quantities? What single complex number tells us both, if this was three-phase S, this is three-phase P, three-phase Q in rectangular form, or this is three-phase apparent power and our power angle. What single complex number tells us the real power, P, reactive power, Q, apparent power, which is just the magnitude, and the power angle? We're just trying to calculate what's the complex power. Now, all the good qualitative context here before we go forward. Notice the problem said the word total. What does the word total mean? Previous problem, we were calculating the per phase values, the values from each individual phase of our bigger three-phase system. Here we have a balanced three-phase load. What is the word total? What are they specifying? They're making sure you absolutely know you're being asked to solve for what? Three-phase. Great job, Daniel. Yeah. We're looking for the three-phase apparent power, three-phase power angle, three-phase real power, three-phase reactive power, the total amount consumed by this three-phase load. In other words, we're not calculating the per phase quantities like the last problem. The word total, when we're dealing with three-phase circuits, implies we're looking for the three-phase values. Does that make sense? All right, so all we got to do is figure out what's the complex power. That gives me the real power, reactive power. It also gives me the apparent power and the power angle. All right, first, let's start in polar form. What's the easiest way I could calculate the three-phase apparent power, the three-phase magnitude? How about this formula right here? I know the line voltage, 208 volts. I know the line current, 10 amps. If I multiply these two together and then multiply them by the square root of 3, I just solved for the three-phase apparent power, which is the magnitude of our complex power. So let's start there. Three-phase apparent power is square root of 3 times the magnitude of the line voltage times the magnitude of the line current. What do we get for the three-phase apparent power? Who's got their calculator handy? I'm typing it in exactly how it appears. Square root of 3, 208, and 10, all multiplied together. All right, what do we got? We could say, look at my calculator, 3,600, I'm going to round to the nearest unit, 3,603 watts. Or if I want to work with smaller numbers, I can call that 3.6, excuse me, not watts, voltamps. Or I could call that 3.6 kilovoltamps. Either answers are acceptable since I didn't specify. When you're working on the FE exam, maybe they're giving you the answer choices in voltamps, maybe they're giving you the answer choices in kilovoltamps. Got to be comfortable with those metric units. Allison said, how do you determine that 208 volts is for phase, not line? Careful, Allison, that's incorrect. Your 208 volts, that's the line voltage. I have a three-phase load. If it doesn't tell me phase or line, or single phase or three-phase, once the problem says I'm describing the values of a three-phase load, I assume everything else is a three-phase quantity unless it says otherwise. That tells me this 208 volts is my three-phase voltage for my three-phase load, also known as line voltage. Yeah, good question to ask about delta Y. You're on the right track, and we're going to talk about that at the end of this problem. Good thinking, though. All right, I've got the apparent power. So that's the first question. How do I figure out the power angle? Where does the power angle come from? Well, I know cosine of my power angle equals my power factor. I know the power factor is 0.85 lagging. So how do I solve for the power angle? Well, I can take the inverse cosine of power factor. Inverse cosine of 0.85. What do we get? So everyone's calculators say 31.788. I'm going to round that to the nearest whole degree. I'm just going to call that 32 degrees. That is the power angle. Now, question, is the power angle positive because my calculator says it's positive? Who remembers from last week? Why is my power angle positive? What tells me that the power angle is positive? Lagging, great job, Greg and Chuck. Yeah, a lagging power factor means that the power angle is greater than zero. The power angle is positive. You can't trust your calculator when you take the inverse cosine. It's up to you to look at, is it lagging or is it leading? Most of the time it's going to be what? Most of the time it's going to be lagging, right? Most loads in real life are lagging. The only leading loads we really work with are capacitors. So maybe you're dealing with power factor correcting capacitors, ultra capacitors, that kind of thing. So most of the time it's going to be lagging. All right, that's our second answer. We got the power angle. Now, how do I get the real power and reactive power? The total amount consumed by the three-phase load. So I need three-phase P, three-phase Q. What am I going to do? Well, do I have complex three-phase power in polar form? Do I have magnitude three-phase power and power angle? I sure do. So I'm just going to use my calculator, convert it to rectangular. I already have the values. It's just like converting, almost like converting units. We're going from kVA and degrees to I'm going to get kW and kvar. So look at this. In my calculator, I'm going to build a complex number. First of all, I'm using kVA. So let's stick with kW and kvar. So I'm going to go up. Here's my magnitude. It's currently in voltamps. I'm going to divide it by 1,000 to convert to kilovolt amps. There's my 3.6. Now I'm going to build a complex number in my calculator. I'm going to go up. Here's my magnitude. I'm going to go into the second complex menu. Here's my angle. And now I'm going to scroll up. I'm looking for my 32-degree power angle right here. I now just entered the complex three-phase power in polar form in my calculator. Again, my calculator, I like to leave it in polar. So if I want to go to rectangular, the easiest way to do that is I'm going to go back to my complex menu one more time. And I'm scrolling down here. A plus BI will say, hey, whatever number that's in polar form, give it to me in rectangular. Convert it for me to do all the heavy lifting on my behalf. What do we get? 3.06. I'm going to say we'll call it 3.1 plus J times, see this arrow here? This arrow means that I can use this arrow in my calculator to tab over, see the rest of the digits. We'll round that to 1.9. All right, what are my units here? If I had 3.6 kVA at 32 degrees, I know this is P, I know this is Q. P is going to be watts, Q is going to be vars, but we're working in kilovolt amps, kVA. So this is really kilowatts. This is really kilovars, right? It's like 3.1 times 1,000 watts, 9.1 times 1,000 bars. That's all. So here is three-phase real power, 3.1. Here is three-phase reactive power. All four of these numbers come from one complex number only. Who can tell me what it is in the chat? One single complex number tells us the apparent power, power angle or power factor, real power P in watts, reactive power Q in vars. What's the single complex number that tells us all of this information? Great job, Chuck. Complex power. Now, where is Allison? Allison was asking this question a couple times in the chat. Wonderful question. Great question. Notice the problem didn't tell us what? Problem didn't tell us, is this a Y or delta connected load? Hmm. Does it matter? Ah, yeah, Allison said I realize it doesn't matter. Yeah, tell us why, Allison. Why does it not matter in this instance? What values were given in the problem? Problem gave us line values, right? Magnitude of the line voltage, 208 volts. Magnitude of the line current, 10 amps. Power factor and power angle, they're equal for per phase or three phase. But if I already have my line values, voltage and current, does the connection make a difference when it comes to power? It doesn't. All of these formulas apply to both delta and Y, right? As long as I know my line values, ignore the connection type, right? The connection type is what's inside of this box. Maybe it's a delta connected load, or maybe it's a Y connected load, but everything outside of this box is line values. I line, V line. Everything inside this box, inside this connection, that's where I get my phase values, phase voltage, phase current. But I'm solving for three-phase power. Who cares? And could I still solve for the amount of power in each phase of my load, or the per phase power, or the power in each individual phase of my three-phase load? Could I still do that without knowing if it's Y or delta? Sure could. I would just divide it by what? Just like we did on the previous page, we would just divide it by 3. That's all. So yeah, has no difference on this problem, Y or delta. Does not make a difference yet. All right, let's try the next problem. Still working with our three-phase power relationships. Example says a balanced three-phase, now it says Y-connected load is rated for 125 kVA and 208 volts. If the load is operating at 50%, we want to know what's the line current equal to. First, my load is Y connected, which already tells me it's what? I already know it's three phase. It's a little redundant, right? Sometimes I'll tell you both. Can I have a single phase Y connected load? Can I have a single phase delta connected load? I can't. I could look at one phase of a Y connected load. I could look at one phase of a delta connected load, but Y and delta, these are three phase connections. So if I have a three phase connection and it says it's rated for blank, the numbers I'm going to assume are what kind of values unless it specifically tells me otherwise. Three-phase load, I'm assuming it's rated at three-phase values. So 125 kVA, that's our three-phase apparent power. That's the three-phase magnitude of complex power. But I can assume that's 125 kVA, three-phase, got a three-phase load. Same thing, if my three-phase load is rated for 208 volts, am I assuming this is a line to neutral voltage for the Y connection, or am I assuming that's a line voltage applied for my Y connection? Three-phase load, I'm assuming, hey, if it just gives me voltage, doesn't say line or phase, then I'm assuming this is a three-phase voltage. I'm assuming this is a line voltage. Yeah, good job, Allison and Gid. So let's just fill in this easy single line diagram. Again, we've got a line voltage of 208 volts. This is a three-phase Y-connected load. It's rated for three-phase apparent power of 125 kVA. And we want to know the line current. However, do I want to know the rated line current? I want to know the line current at what? What's the line current when this load is only operating at 50%? Here's how we do that. First of all, I know I got to get the line current first. So I'm looking at which of these formulas is the easiest to use for line current. Remember, throw this formula out. It's trash. It's garbage. You're never going to need it. It's just going to make mistakes. So, these are magnitudes because it solves for the apparent power. Do I know my line voltage magnitude and my line, excuse me, do I know my line voltage magnitude and my three-phase apparent power? I sure do. So the only thing left to solve for would be the line current magnitude. So I'm using this formula right here. Three-phase apparent power, three-phase magnitude, complex power equals square root of 3 times line voltage magnitude and line current magnitude. So let's try that first. Solving for my line current. Line current equals three-phase apparent power divided by square root of 3 times line voltage. So we're using this formula, but we're solving for the line current magnitude. We have everything else is given to us. So line current magnitude equals, we've got, again, three-phase apparent power on top divided by square root of 3 times the line voltage magnitude. All right, what was the apparent power this load is rated for? This load is rated for how much? 125 kVA. Square root of 3, that's just a coefficient, times our line voltage. How much is our line voltage? That's 208 volts. So what we're solving for right now, we're solving for first, we're solving for the rated line current, the 100% line current. What do we get? If this machine was operating at 100% load or rated conditions, what would the line current be? So fraction sign, 125 kVA is times e to the 3. E to the 3 is your times 1,000, it's your K. Divided by square root of 3 times 208 volts. We get about 347.0, excuse me. So we have a line current magnitude at 100% load or rated conditions, 347.0 amps, just rounding here. If that's the 100% line current or the rated line current, how do I figure out, hey, what's the line current instead if the load's only operating at 50%? What do I do? Real easy. Well, this is my 100% line current. So I'm just going to multiply that value by 50%. Or I'm going to multiply it by 0.5, or I'm going to divide it by 2. Same thing. If 347 amps is our 100% operating line current, then that value times 50% is how much line current the machine's going to draw instead at 50% load. Final answer, 173.5 amps. Everybody with me so far? Really easy stuff. Don't let that operating at 50% scare you. Good job. Good question from, is it Esther asked, how do you know that the given 125 kVA right here, how do we know that's apparent power, not real power? Who can tell me what's the unit of real power P, Esther? Unit for real power P, this is watts. Yep. What are my units for Q, reactive power? This is vars. Maybe, watts or kilowatts, vars or kilovars. That's just a times 1,000 multiplier. What are my units for apparent power? What's the magnitude of P plus JQ? Magnitude is vars. Excuse me, not vars. Magnitude is voltamps. A little bit of a tongue twister this morning. Apparent power is voltamps. Real power is watts. Reactive power is vars. So we've got 125 kiloVAs, which just means 1,000 times 125, but we're still working with voltamps. That tells us it's the apparent power. How about this? What if the question asked, solve for the apparent power drawn at 50%? How do we solve for how much apparent power the load would consume at 50%? It's rated for 125 kVA, meaning at full load rated conditions, we can expect 125 kVA. But if it's operating at 50%, All we do is we would just multiply this number by 50% as well. I could say 50% times 125 kVA means if I'm drawing 173 and a half amps at 50%, I'm also drawing 62.5 kVA when it's operating at 50%. Otherwise, at 100% load, this machine's going to draw 347.0 amps and it's going to draw 125 kVA. The operating percentage, you multiply it directly to your line current and your power. All right, what would happen if the load was delta connected instead? Any change to this problem? Where's Allison? Any change? Yeah, no change. Why not? Nothing would change. Why not? What kind of values are we working with? We're given our line values. So we don't need to really know if it's delta or Y connected. Problem said Y connected. That's what we call what? That's what we call red herring. Maybe that sends us on a wild goose chase. I'm looking at the reference handbook I'm looking at my, Y formulas where V line equals square root of 3 times a V phase, but I don't have a V phase value here. Don't need to know it. Or I'm looking at for a Y connection, I line equals I phase. That doesn't really help me here. All right, let's see. We'll go for about 10 more minutes. It's 1:20 p.m. here on the East Coast. We'll see how far we can get for 10 more minutes, and then anything that we don't finish, we'll start with next week. All right, now we have an example of a delta connection. We'll see if this changes anything being delta connected. So we got a balanced three-phase delta connected load. It's rated for a phase voltage, very interesting, of 120 volts. It says phase voltage, and a very interesting phase current of 10 amps. Determine the total amount of three-phase apparent power drawn by the load at rated conditions. First of all, what does this word total mean? Total tells us they're asking for what? Three-phase. Great job, Daniel. Yeah. And it tells us again here, total amount of three-phase apparent power. They could have just said, what's the total apparent power? Same thing. Rated conditions tells us what? We don't got to worry about scaling anything up or down. We're just using rated values. So let's fill in our delta connection here on the right with anything given the problem, and we'll see if we can figure this one out. So a delta connected load is rated for a phase voltage of 208 volts. I can say that's phase voltage equals 120 volts from A to B. Same phase voltage from B to C. Same phase voltage from C to A. And we have a phase current of 10 amps. Here's the phase current of 10 amps from A to B, phase current of 10 amps from B to C, phase current of 10 amps from C to A. All right, determine the amount of three-phase apparent power drawn by the load at rated conditions. So we're looking at like, okay, I'm given individual phase values, but I'm looking for what's the total amount of three-phase apparent power drawn by all three phases. All right, a couple of different ways we can solve for this. First is I'm looking at my three-phase formulas. Remember, these are three-phase formulas, even though they just use magnitude S. It's really magnitude three-phase S. Look at this right here. Three-phase apparent power equals 3 times my phase voltage magnitude and phase current magnitude. Do I have these two numbers, phase voltage, phase current? Yeah, I sure do. So we're going to try solving for it this way first. Magnitude three-phase, The total three-phase apparent power equals three times what's our phase voltage across each phase is 120 volts times phase current is how much in each phase? 10 amps. What do we get in our calculator? What's 3 times 120 times 10? We could say three-phase apparent power equals, I could say this is 3,600 volt amps, or I could say this is 3.6 kVA. Same exact thing. See if we get a nice square. There we go. All right, that's one way to do it. What's another way to do it? What if I converted my phase current to line current? Here's my A phase conductor. How would I solve for the line current traveling on this conductor? For a delta connection, what does the line current equal? Line current is bigger by a factor of the square root of 3 times the phase current. So I'm going to take the phase current given 10 amps and I'm just going to multiply it by square root of 3. So square root of 3 times 10, it's going to be what? 17.3. See if I can get this in. There we go. 17.3, right? How to know that? Square root of 3 is about 1.73. 1.73 times 10, 17.3. So we got a line current of 17.3. Now, could I use this following formula? The more common formula, three-phase apparent power equals square root of 3 times V line times I line. Could I use this formula now? Should get the same answer. Square root of 3 times, for a delta, line current equals square root of 3 times phase current. What does the line voltage equal for a delta connection? They're the same. They're equal. So line voltage equals phase voltage. So line voltage is going to equal to our phase voltage times what's our line current we just solved for? 17.3 amps. What do we get? So my calculator, I'm going to say square root of 3 times 120 times 17.3 amps. Look at that. Same answer. Three-phase apparent power equals 3,600 volt amps or 3.6 kVA. Same thing. Like that? Here's a great question. This was a delta connected load. What if this was a Y connected load? Hmm. What if this was a Y connected load? Hmm. They gave phase voltage and phase current. What if this was the same problem, but the only change instead of delta connected? What if I had a Y connected load, phase voltage of 120 volts, phase current of 10 amps? Ah, it would be the same. Why would it be the same? Previously, I just told you, hey, if you're given line values, it doesn't matter. If you're given phase voltages that or phase values, that's where you got to be careful. Why does that not necessarily apply here? Same formulas for line values. So if you look at this, like for a Y connection, the line voltage is bigger by square root of 3, but the line current is equal. So first of all, there'd be no change to this formula. 3 times phase voltage, phase current, we'd still get 3.6 kVA. Over here, there would be no change to our 10 amps, but that square root of 3 multiplier would then apply to the voltage instead. So you end up getting the same values. It's a really great exercise to practice. All right, let's see if we can knock out the next. Well, how about this? We'll do the next two examples. We'll go a little bit over, and then we'll save the phasor diagram for the start of next week. All right, interesting set of problems and formulas in the reference handbook. So, reference handbook says for a three-phase Y and delta connected loads. Look at this. Remember, they don't do a good job of specifying complex or magnitude. They don't do a good job of specifying three-phase and single phase. So get in the habit of writing it down. This is complex three-phase power equals the square of the line voltage divided by the conjugate of the Y impedance. This is a complex number. The voltage is just a magnitude. Or complex three-phase power equals 3 times the square of the line voltage once again, divided by the conjugate of your complex delta impedance. When you get to the P exam, there's also another set of formulas, S equals I squared times Z. This is just the voltage version of these formulas. Which one of these can I use for a Y load? Which one of these can I use for a delta load? How about this? The one on the left, can I use that for a Y load or a delta load? One on the left, I can use that for a Y load. How do we know? I got the Y impedance on the bottom. The one on the right, I can only use this for a delta load because I've got a delta impedance on the bottom. Who can remember what's the relationship with Z delta and ZY? Sometimes you might have to use this with these formulas. I can say complex Z delta equals 3 times complex ZY. And I've included some Y relationships and Y formulas we've already discussed that we're going to use. Let's try it. Determine the total complex power consumed by a balanced three-phase Y connected load. That tells me I'm probably using this formula on the left with an impedance of 20 plus J5 ohms per phase. System is supplied with a phase voltage of 120 volts RMS. This time specifying that it's RMS, but 120 volts, we should recognize that by now. All right, fill in the diagram. ZY in each phase equals how much? I've got 20 plus J5 ohms in phase A from A to B, or A to neutral, phase B, B to neutral, and phase C, C to neutral, 20 plus J5 ohms in each phase. Now, the voltage. Is this my line voltage that I'm going to plug into this formula? If I have a Y connected load and it says phase voltage. This is my line to neutral voltage. So here is plus V phase equals 120 volts from A to neutral. So before I can use this formula that uses the line voltage, I got to convert my phase voltage to what? I can't use the voltage from A to neutral. I got to use the voltage from A to B, my line voltage, which for a Y connection is bigger by the square root of 3. So magnitude V line, that's going to be square root of 3 times our given phase voltage, 120 volts. What do we get for the line voltage? What's the square root of 3 times 120 volts? It's a common three-phase voltage, 208 volts. There's our line voltage from A to B, B to C, and C to A. Now I'm ready to use my formula for three-phase power for a Y connection using voltage and impedance. Three-phase complex power equals, we're going to take our line voltage, we're going to square it, we're going to take our complex impedance, and we're going to use the what? We're going to use the conjugate. All right, how much total complex three-phase power? Let's find out. Back in my calculator, I'm going to take this last value, I'm going to square it, I'm going to put it on top of a fraction. My Y connected load is 20 plus J5, but I got to apply the conjugate. How do I apply the conjugate to this load? What do I got to change? What's my cursor on my calculator hovering over? Just like we talked about changing the angle, if it's positive, then you make it negative. If it's negative, you make it positive if you apply the conjugate. How do I apply the conjugate to a number in rectangular format? Same thing. If it's positive, make it negative. If it's negative, make it positive. Not the overall complex number, but just the polarity of the reactants or the imaginary component. I have plus J5 to apply the conjugate. I turn that plus into a minus. All right, let's see. In polar, we've got a complex three-phase power of, I'm going to use kVA. So we're going to call that 2.1 kVA at an angle of, say, 14 degrees. Or in rectangular, maybe they ask for P and Q instead. That's the same thing as, we'll call that 2.0 kW plus J times, we'll call that 0.5 kVAR. Really easy to formula to use. You just got to watch out for your conjugate. Make sure you're using the right formula if it's a Y or delta connected load. See if I can get a rectangle here. There we go. And you got to make sure you're using the right line values only. All right, I think last example for today, and then we'll stop on phasor diagrams and we'll start back up there next week. All right, same set of formulas, right? Remember, these are complex numbers, but the voltage is just a magnitude. Got to know that to use it correctly. This time we have a balanced three-phase delta connected load, draws 5 kVA at a power factor of 0.90 lagging. Interesting, this time they're giving us the complex power. If the system is supplied with a line-to-line voltage of 408 volts RMS, determine the impedance of the load. Interesting. So now we're given complex S, we're solving for complex Z. Let's see if we can do it. So here's my delta connection. We've got a line-to-line voltage of 480 volts. That's the same as what? I can call that V phase. I can call that V line. Same thing because it's delta connected. And I've got that from A to B, B to C, and C to A in each phase. We're trying to solve for what does Z delta equal, but I'm also given the total three-phase complex power. So that tells me I can use my S equals V squared over Z formulas. Which one am I going to use? Am I going to use the one on the left that use a Y impedance, or am I going to use the one on the right that uses a delta impedance, which is the value we're solving for? Delta connected load, you got it, Daniel and Chuck, which means we're going to use the delta version of this formula. Reminding ourselves this is not apparent power, it's not the magnitude, this is three-phase complex power. This is the conjugate of our complex impedance, and this voltage, that's just the magnitude. All right, first things first. Let's get our power angle from the power factor using this formula right here. Power factor equals cosine theta. I know theta equals inverse cosine of power factor. Inverse cosine of our lagging 0.90 power factor. What do we get for the power angle of this delta connected load? So we get about 25.8 degrees or 26 degrees, depending on how you want to round. Is this power angle positive because my calculator said it was positive? Is my power angle theta positive because this number is positive? I'm going to always ask you this when it comes up. It's one of the easiest and most common sources of wrong answers. Good job, Jeff. Jeff said it's positive because it's lagging. Theta is greater than 0 degrees. Theta is positive when the power factor is lagging. All right. Do I have my complex three-phase power? Hmm. 5.0 kVA. It doesn't say it's apparent power, but volt amps I know is the magnitude of complex power. And now I've got the angle of complex power. So I've got this number. I've got this number. That's 480 volts. I'm solving for this number. So I'm going to rewrite this formula, solving for the conjugate of my delta connected impedance. Notice there's a 3 here on this formula, which does not show up on our Y connected formula. All right, rearranging this formula, solving for complex Z delta conjugate. All we're going to do is replace Z with S. So we have 3 times the square of the magnitude of our line voltage divided by the complex three-phase power. All right, let's plug in some numbers. 3 times, that's just a coefficient. The square of our line voltage. Notice the problem could have said a phase voltage, and that wouldn't have made a difference because it's a delta connected load. V line equals V phase. All right, now we're plugging in our complex three-phase power. We got the magnitude, 5.0 kVA. We've got the power angle. We just solved for that, right? 25.8 degrees. We're going to type this in our calculator, and it's going to give us the conjugate of our delta connected impedance. All right, so in my calculator, I'm going to type in just how it appears on my paper. 3 times fraction sign, 480 volts squared, divided by, I've got 5e to the 3, that's kVA, at an angle of 25.8 degrees. I'm in polar mode. I want this number in rectangular because that's more often how we represent impedances. So the conjugate of the delta connected impedance is about 124.4 minus J times, we've got about 60.3 ohms. Is this my final answer? I've got one more step to do. If we're asked to determine the impedance of the load, we weren't asked to determine the conjugate of the impedance. We're asked to calculate just the impedance. So how do I get rid of this conjugate sign? This is negative. I'm going to make it positive. If that was positive, I would make it negative. We're just changing the polarity of the reactance, which is the imaginary component of our complex impedance. All right, 142, we went a lot longer than I'd planned. Sometimes, these examples I think are going to be real quick. A lot of times we get into good discussion, so I hope at least you guys enjoyed the question and answers. Any questions before we take off? And then next week, we'll look at these relationships in the reference handbook, line to neutral phase voltages, line to line voltages. We'll talk about these phase shifts, how in a balanced and positive sequence system, all of our phases are displaced by negative 120 degrees, but then the line voltages are displaced by 30 degrees. And then we'll draw out a phasor diagram together using a reference angle of 0 degrees for our A to neutral voltage. We'll use just our A to neutral voltage to figure out A to B, excuse me, B to neutral, C to neutral. And then again, we'll use our A phase voltage to get our A line voltage, B line voltage, and C line voltage. And then we'll also look at a quick example of what happens if we don't have a reference of 0 degrees for our A phase voltage, which is more common. But if I got something crazy like negative 35 degrees for A to neutral voltage, do all of these relationships still apply? Of course they do. And really, how we can use this information as a roadmap. This is going to be your bread and butter. FE exam, easy. Once you pass the FE exam and you're ready to buckle down and take the more challenging P exam, this is going to really help having a strong foundation. This is your bread and butter for the P exam, complex numbers. All right, any questions before we get out of here? Any questions? Good. Just about all of you are still here, made it to the end. Again, I apologize when we go over by an hour, the hour time slot. Sometimes just have so much information to pack in. And the good news is if you can't attend for the whole hour, all the recordings, of course, will be available. So you can always catch up after the fact. Excellent. All righty. Give me a quick 1 to 5 in the chat. How are we feeling on the three-phase power relationships we worked today, including delta and Y? 5 being the best, if you're feeling the most comfortable. 1 being you're still really struggling with it and need a lot more practice. Good. 5 from Chuck, Jennifer, Jeff, Niraj, Jean's iPad, Olua, Maurice, Oscar, Gary, Gabriel, Damon. Great. All 5s. Wonderful. Yeah. End of the day, I'm telling you, the concepts on the FE exam, it's really an inch deep, mile wide. Focus on the real simple examples. Even if you get a really hard example you can't answer, that's fine, but you're going to get the other simple ones right in other subjects. Much more productive strategy for passing the FE exam. FE exam, it's easy stuff, right? No need to lose sleep over the FE exam. Work as many simple examples as you can, and you'll be just fine. All right, everybody. Next week, we're going to pick up where we left off. We're going to look at these phasor diagrams, and then we'll also start on transformers. I believe next week is on Thursday, so check your calendar. Make sure you're signed up on that Zoom registration page if you're not already. All right, everybody, thank you so much for attending, and I'll see you next week. Take care.